Measurements. So before I go directly into measurement, I want to give some examples about the conversions in the units that are very important before that I mentioned. And yes, before I forget, there is also a part, remember we introduced the fundamental quantities, the derived quantities, and the fundamental units called base units or base quantities. Derived quantities and the derived units. There is also another family of quantities called the supplementary quantities. The supplementary physical quantities are sometimes attached to the fundamental, but they are not really part of fundamental because they have no dimensions per se. They are used to measure certain properties of angles. And one is the plane angle, and the unit is a supplementary unit called the radian. Okay, the plane angle is like this in 2 dimensions, theta. Okay, this is a plane angle. Okay, then we have the solid angle measured in steradian. Remember, we saw this steradian thing when we were defining one of the units we defined before. So these two are called supplementary physical quantities. They have no dimension. So their dimensions of each of them is 1. Because actually, this is S over R. We're going to come to this. They are both, it's a ratio of lengths. It's some kind of angular measure we call the radian. We'll discuss it more when we discuss the circular motion or the curvilinear motion or angular motion in the plane. Yes. They are very important in describing the curvilinear motion. We say solid angle. It's like when you draw a cone in 2 dimensions, this is the angle. It's like a triangle. But when you draw a real 3-dimensional cone, you see that the angle inside is like a cup, a circular cup, like a cap, like a hat, like this in 3 dimensions. So the angle inside is also like this. That angle inside is a solid angle. So it's like a 3-dimensional kind of angle, okay? Okay, not just a plane angle, which is the radian, okay? Now, I want to take some examples before we go to measurement. And then, like I said, when we come to the angular motion in a plane, yeah, which some people still call curvilinear, okay, because they feel that you can express those curved properties in linear terms, okay? But we'll explain better when we get to that side of the topic. So for now, I want to talk about let's take an example in the conversion, okay? Say convert 36 kilometers per hour to meters per second, okay? That's one. Number 2, convert 20 centimeters per second to kilometers per year, okay? Or convert 500 milliseconds to megaseconds, okay? Okay. In milliseconds, megaseconds, okay? So we can convert from anything to anything. So let's start from the first one, number 1, okay? Say convert 36 kilometers. So this will tell us how to convert. We write the unit like this, kilometer per hour. Then I look for what is what. I want to convert this to meters per second. So instead of kilometer per hour, I want meters per second. So I go stage by stage. Okay, since I want meters per second instead of kilometers per hour, I replace the up with meters. How do I do that? 1,000 meters is 1 kilometer. 1,000 meters is 1 kilometer. So kilometer, we cancel kilometer. Meters is left up. And then 60 seconds is 1 minute. Okay, so let me go stage by stage on that. Let me not just say it like 3,600 seconds is 1 hour. Okay, I'll tell you how that is. Let me get where's this eraser I used just now. So I'll erase this just to make it clearer and give more space. 1 hour is 60 minutes. Hours cancel hour. Now I have meters per minute. But I want meters per second, not meters per minute. So I convert minute again. 1 minute is 60 seconds. So minutes cancel minutes. So what I have left is meters per second. But I have to multiply all of this. So this is 36 times 1000 over 60 times 60. So this is 36,000 over 3600. Okay? Okay? This will give us 10 meters per second. Okay, that's how we convert. We just cancel what we want from the top and the bottom just until we get the unit we want. Be careful, whatever you want at the top is what you put at the top, okay? And convert 20 centimeters per second to kilometers per year. That's the second one. 20 centimeters per second. So I can convert centimeters first. So I have 1 meter is 100 centimeters. So centimeters cancel centimeters, but I want kilometers. 1 kilometer is 1000 meters. So meters cancel meters. I already have kilometers on top. Now I want to convert seconds to year. 60 seconds is 1 minute. Seconds cancel seconds. I want year, not minutes. So I multiply again times 60 minutes is 1 hour. So minute cancel minute. Times 24 hours is 1 day. Hours cancel hours. Times 365 days is 1 year. So leap year 366 days, but we'll just assume 365 days. Okay? So when I multiply everything, 20, okay? Times 60 times 60 times 24 times 365 divided by 100 times 1000. Okay? This is going to give me 2102.4 kilometers per year. So as you can see, everything has cancelled out from everywhere except the kilometers and the year. Okay? Except the kilometers and the year. Good, good, good. Now let's convert the third one. 500 milliseconds to megaseconds. Okay? So this is 500 milliseconds times 10 to the minus 3 seconds. If you look at the table we drew for the submultiple of units, is 1 milliseconds. Okay, so milliseconds cancel milliseconds, we have seconds, but we want megaseconds. So I know 10 to the 6 seconds is 1 megasecond. Okay? Okay? I have to flip that around because I want the seconds to cancel. So 1 megasecond is 10 to the 6 seconds. Okay? So seconds cancel seconds. All I have left is megaseconds. So it's 500 times 10 to the minus 3 divided by 10 to the 6, which is 500 times 10 to the minus 3 times 10 to the minus 6. Okay? And that will give us 500 times 10 to the power minus 9. In measurement, there are a lot of ways to measure length or distance depending on the kind of length you want to measure. So we're going to start from measuring length. And measuring length, we use meter rule. Okay? Some of you have seen a meter rule before, and I'm going to show some images for you on the screen for you to see. So it's 1 meter long, which is 100 centimeters, okay? Calibrated in centimeters and small millimeters in between. So it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. So this is all centimeters, 1 centimeter, until you get to 100. 100 centimeters. That's 1 meter. Okay? So there is something we call reading accuracy of a measuring device. Any measuring device, all measuring devices in physics have a reading accuracy. So reading accuracy simply means the smallest graduation in that equipment. It means the smallest reading you can get from that equipment or that device. Okay? So what is the smallest thing a meter rule can measure? Is a millimeter. 1 millimeter. 1 1 millimeter, 0.1 centimeters. This is the reading accuracy, I'll just call RA, of a meter rule. If you get smaller than a millimeter, you see we have 10 millimeters here, that makes 1 centimeter. So from 0 to 1, it's 10 millimeters. From 1 to 2, another 10 millimeters, like that. So anything smaller than 1 millimeter, the meter rule cannot measure. The meter rule cannot measure accurately. Okay, we'll come and see the kind of errors we can get from there as we go along. So reading accuracy of a meter rule, the smallest reading you can get from a meter rule is 1 millimeter or 0.1 centimeters. Okay? And there's a very common error people make when using a meter rule. It's called the parallax error. And it is the error you get by looking at an angle to a reading. So when you want to take a reading from a meter rule, you're supposed to look directly at that point, not at some angle. You might get the wrong reading because of how close these millimeters graduations are to each other. Okay? So it is called parallax error. Error due to parallax error. Okay? So when we are using a meter rule, we try to avoid parallax error by making sure that our eyesight is vertically opposite the direction or the point we are taking the exact reading. Okay. Okay. You can see an image of a meter rule on your screen. Now, let's talk about what we call the Vernier caliper. Actually, before the invention of the Vernier calipers, there were some other calipers that were used. They're called the open and closed calipers. They are used to measure the diameters of tubes, either internal diameters, okay, or external diameters, like that, okay, or external diameters of tubes, like that, okay. So this for external diameter, this for internal diameter. It goes in. So you take it out, you touch the edge, you take it out, you touch the ends of the outside one. This is the internal one, and this is the external one. You touch the inside, then you place it on a meter rule to view that reading that you have just measured. You place it on a meter rule to see that reading. You place it on a meter rule to see that reading. Okay, you can see that on your screen too. But the Vernier caliper combines both of those and has what we call a main scale and a vernier scale. So the Vernier caliper uses the main scale and the vernier scale combined together. So the Vernier caliper, because it measures smaller distances, it is designed in a way that the reading accuracy, the smallest graduation, is more than that of the meter rule. So the reading accuracy I call RA for a Vernier caliper, okay, is 0.1 millimeters. So which is one less, so it's 0.01 centimeters. So when we want to measure the external diameter, okay, of something, of some tube, we place the tube in here, as you can see on your screen, or the internal diameter of something, we look at the main scale and the vernier scale. So the vernier scale is down here, and the main scale is up there. So let's say after that, I'm going to magnify this, okay? So we have 1, 2, 3. So this is 2, 3, 4, 5. So this is 1, 2, 3, okay, 4, 5, 6, 7, 8, 9, 10. So when you measure this, this will give us 2.2, 2.123, I mean 2.3 before the vernier scale started. So this is the main scale. So we combine the reading from the main scale and the vernier scale. So we have this, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 3 like that, 3.5, and it goes like that. Okay? Can you zoom into this a little bit, please? So the students can see this clearly of what I want to see or what I want to explain. So you see, here the main scale ends at 2.123 centimeters. So I'm going to do this in a table or for you to see. So this is going to be centimeters and millimeters. I'm going to do the calculation in both. So I'll take the main scale reading, the vernier scale reading, the Vernier scale reading, and the total reading. Okay? So the total reading is what I'm going to use as the actual reading. Before the Vernier scale started, the main scale read 2.3 in centimeters, 2.30 centimeters. The Vernier scale, I'm going to see where a mark of the Vernier scale intersects with a mark on the main scale. This doesn't intersect, this doesn't intersect, this doesn't intersect. It intersects at 5, the fifth mark. Okay? The fifth mark on the Vernier scale. So that will be 0.05. So because in centimeters, it has a reading accuracy of 0.01. Okay? And this one measures in millimeters. The Vernier scale is in millimeters. And the main scale is in centimeters. So I sum this up together to get my total. My total becomes 2.35. So that part that was missing was 0.5. That part that the main scale could not read, the Vernier scale tells you that part. Okay? By looking at the line, it could intersect with the 6, 7. Any the line it intersects with is the one you add. So in millimeters, this will be 23.0 plus, okay, this will be 0.5. So this is 23.5 millimeters. Okay? You can always go from centimeters to millimeters. Okay? That is a Vernier caliper and how it works. We have one more for measuring the diameter of thin wires called the micrometer screw gauge. Okay? The micrometer screw gauge records more precise results than the Vernier caliper. Okay? Some people say it can be used to measure the diameter of thin wires. Some people say even thin hair. Okay? Not so sure about that, but they are very precise. So it has the micrometer screw gauge. The micrometer screw gauge number 3. Okay, it has a sleeve. Okay, that you put in between that thing and you screw it up. As you can see, you screw that screw. You can see on your screen, you measure the diameter, just external diameter of very thin wires. So it has a reading accuracy of 0.001 centimeters, okay, which is 0.01 millimeters. So it's more precise than the Vernier caliper, and the Vernier caliper is more precise than the meter rule, like that, okay? So it combines a reading from the sleeve, which is the main scale, and it has a rotational scale that you rotate here, that's we call the Vernier scale, okay, like this. So this is 1, 1.5, 2, 2.5, 3, 3.5. So this 0, okay, let me put this 0, okay, 1, 2, 3, okay. And then this scale goes down here like this. Some of them go to 50, some go to 100, depending, but they all measure the fraction of a millimeter, okay? Now, in this part, okay, I want to see where this meets this line. So we're going to have some readings here. So this is 20, 21, 22, 23, 24, okay? This is 25. 26, 27, 28, 29, this is 30. So it goes like that, okay? So I have all these numbers there. So I'm going to use here again, okay? I'm going to have main scale reading, Vernier scale reading, or the thimble reading, they call it. The reading on the thimble, this is the one that rotates. Okay, I would like you to zoom in here also for the students to see what I'm going to do right there. Okay, for the thimble reading. So the main scale reading is 3.00 millimeters. 3.00 millimeters. And what is the Vernier scale reading? Where it meets this line. 20, 21, 22, 23. 24 is where this line from the main scale intersects with the Vernier scale on the thimble reading line. So that will give me 24. That's 0.24 millimeters. So I add them together, it gives me 3.24 millimeters. So in centimeters, it's going to be 0.30, okay? 0.300 plus 0.024. 0.324 centimeters. So it's the main scale reading plus the thimble reading or the Vernier scale reading, main scale reading. So this one is in centimeters and this one is in milliliters. So always work with the reading accuracy to see how to measure this. We can see more examples later as we solve problems, but I'm just going through this a little fast, okay? Okay. Then here, the next thing I want to make mention of to you guys is that I can give an example. I say, for example, I say, name the device used for the following measurements. So they want to see if you understand the reading accuracy. So number one, I have 3 centimeters. Okay? Okay? I said 3 centimeters. Okay? Or let me say 3 millimeters. Number 2, 2.0 centimeters. Number 3, 2.0 millimeters. Number 4, 3.91 millimeters. Okay? Number 5, 21.397 centimeters and 1.397 centimeters. Like that, they'll give different readings. Okay? So they say which devices measure this? From which devices? 3 millimeters. So it measures 1 millimeter. So which device has a reading accuracy of 1 millimeter? That is a meter rule. A meter rule is the one that has 1 millimeter. So a meter rule must have been used here, because the reading accuracy of a meter rule is 1 millimeter. 2.0 centimeters. So it is 1 decimal point in centimeters, which is the same as 1 millimeter, because a meter rule is 0.1 centimeters also, which is 1 millimeter. So this is also a meter rule. 2.0 millimeters. 1 decimal point in millimeters, 0.1 millimeters. That has to be a Vernier caliper, because it has a reading accuracy of 0.1 millimeters, 1 decimal point. 3.91 millimeters. This is a micrometer screw gauge, because it has 2 decimal points in millimeters. And 3 decimal points in centimeters is the same as a micrometer screw gauge, because 3 decimal points in centimeters is the same as 2 decimal points in millimeters. So 0.01 millimeters, which is the same thing as 0.001 centimeters, that is the reading accuracy of a micrometer screw gauge. So 3 decimal points in centimeters or 2 decimal points in millimeters, both are micrometer screw gauge. So you can see from the reading, you can tell from what devices these measurements were taken. And then we have other devices for measuring time, like the stop clock, the wall clock, the wristwatch. Okay, and we have many which we are displaying on the screen for you. Then we also, after measuring time, we are going to go into measuring mass. We have the different scales, the beams, okay, and the balances that are used to, the weighing balances that are used to weigh mass, the mass of an object in grams and kilograms. And then for weight, we have the spring balance that gives you the actual weight in newtons instead of just the mass in kilograms. So we have all these devices in the laboratory, so these measuring equipments that we use to measure mass, even volume. We use the tubes, okay, we have test tubes, we have volumetric tubes, okay, that we use. We call this the cylindrical, they call them the volumetric cylinders, okay, the volumetric cylinder, or measuring cylinders. For measuring, they are calibrated in centimeters cube, milliliters cube for measuring volumes. Okay, then for solids, to measure volumes of solids, you can just take the dimensions. If it's a regular solid, like if I have something like this, I want to measure the volume, is a regular solid like this, okay? So if we have something like that, like a cuboid, they call it, so I have the length, the width, and the height, okay? So I say length times width times height gives me the volume. But if it's some irregular solid, I want to measure the volume like a stone. So we have what we call the Eureka method, okay? Okay? So we can use the Eureka method, or we can use the simple displacement method to measure the volume of an irregular material. I'm going to explain that right here. I'm just going to run this a little bit too fast because we don't have much time, and I still have to discuss errors with you. The introduction is just a lot of information right now, and I'm sorry about that. But now, if I want to measure the volume of an irregular solid, volume of an irregular solid, like a stone, okay? One way is to get a measuring cylinder that we know the volume that's calibrated. So this is 50 centimeter cube, for instance. I insert, it has water or fluid. Then I insert the stone inside. You see the water will rise up, okay, to say 55 centimeter cube, okay. So the water has risen up when the stone goes into 55 centimeter cube. So the difference here, del V, 55 minus 50, 5 centimeter cube, becomes the volume of that stone. So that is one way of knowing the volume on a calibrated measuring cylinder. But if I don't have a measuring cylinder, so that's when we use the Eureka method. We take a tube. The Eureka is like a cylinder that has a hole like that, okay? And then we have here a measuring cylinder, okay? So here we put the water up to this extent just to go over. Then we put the stone inside, so it will displace the water, and the water comes in here and collects. Then we measure the volume of this water that is collected. That becomes the volume of the stone or the object. They are both called displacement methods. You just put the object to displace some water or some fluid that you can easily tell the volume like that. Okay? Then we can measure area. We have different ways of measuring area, different ways of measuring different things. Okay? And when I was introducing you, there are some difficult situations in the introduction of the different parts of physics we have, different areas of studies in physics. There's an area called plasma physics. They go to the ionosphere, they perform experiments using certain gadgets, okay, taken up there. So these experiments try to measure the ions and interactions of those plasmas there. It's a very difficult situation to do an experiment. They collect data, they analyze the data on Earth, and from there they get useful results that helps in planning, satellite launching, and also spacecraft dynamics also. Okay, now we have discussed measurement to some large extent, okay. Now let's talk about errors. I'm going to be very fast in describing error analysis, okay, so pardon me, talk about error analysis. So the thing is, I explained before, every measurement has an error or some kind of uncertainty, we call it. Okay? And since we have these errors, an error is actually defined as the amount by which a measurement value deviates from a true value. So we know a true value, and you measure the same thing, you get a value slightly different. By how much does your value you measure differ from the one we know to be more accurate, to be the true value? Okay? Okay? I'm going to give an instance. And that's what we call the error. So we measure length, say 2.0 meters. We usually add plus or minus 0.1 meters. So this plus or minus tells us the error range. So this is the measurement and this is the error. So for significant figures, when you take a decimal point for your measurement, you use the same decimal point, okay, the position of the decimal point for your error. So for instance, I cannot say 2.67 centimeters plus or minus 0.1 centimeters, or 2.67 plus minus 0.1, can put the unit outside centimeters. So this is two decimal points or two decimal places. This is one decimal place. So your error has to be the same decimal places as your measurement, okay, for consistency. So we just say 0.10. So now it's correct now because it's two decimal places, two decimal places. So you have to watch out for these significant figures, okay? So when you say plus or minus 0.1, it means it could be 1.9 or it could be 2.1. So it is somewhere between here. It gives a range of values that you think that you have made an error around it. So it gives that range of values. I'm going to tell you how to calculate that error in different circumstances or different situations. Yes. So there are lots of errors we're going to look at. But before we start, every experiment we do in physics, our aim is to be both precise and accurate. So we talk about accuracy and precision. Okay, what is accuracy and precision? Okay, I'll give an example to explain accuracy and precision. So take a look at this. Right now, I want to tell you the difference between accuracy and precision. Let's say I have Bob and Alice, okay, trying to measure acceleration due to gravity g, which we know to be 9.8 meters per second squared. Okay, so they performed an experiment 5 times and they got 5 different values. So Alice got 9.0 the first time, 9.0 the second time, 9.1 the third time, 9.2 the fourth time, 9.2 the last time. And Bob got 8.9 the first time, okay, 9.3 the second time, 9.7 the third time, 10.1 the fourth time, and then 10.5 the last time. Okay. Now what we're going to do, we're going to sum this up and get an average. An average here is 9.1, average here is 9.7. Okay. And then the question is, whose values were close to each other? How can you, whose values you can tell was trying to measure the same thing? Alice, because she had 9 point something. But Bob had values varied from 8, 9 to 10. So the person's values that were closer to each other, that you could tell was trying to measure the same thing, is more precise. So Alice was more precise than Bob. Now, let's look at what we are looking for. We want to measure acceleration gravity, 9.8 meters per second squared. After taking the average, whose value was close to 9.8 meters per second squared? Bob, 9.7. So it means Bob was more accurate. Bob's result was more accurate than Alice's result. So sometimes you can be accurate but not precise. Sometimes you can be precise but not accurate. But our aim as physicists, as experimentalists in the lab, we want to be both Alice and Bob. We want to be both precise and accurate. Okay? So we want to be Bob Alice. Okay? Now, I'm going to mention to you some very common errors in the laboratory. I'll go into details of a little bit. I'm not sure if I'll have time today to go into the normal distributions and how they work in calculating the standard deviations and how you can tell, but I can give a few minutes of description of that, and you can read more about that, okay? So I'm going to measure some types of errors. Some types of errors. So I can start reading error. Number 2, estimated error. Number 3, statistical error. Number 4, standard error. Number 5, fractional error. Number 6, relative error. Okay. Number 7, absolute error. Number 8, percentage error. Number 9, we've talked about parallax error before, you know what that is. Number 10, talk about systematic errors. Number 11, erratic errors. Number 12, talk about blunders and mistakes. 13, indeterminate errors. 14, we can keep going and going. There are lots and 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 lots of errors. Okay, I cannot mention all of them, but they are there. Okay, we can have random errors like that. Okay, now I'm going to discuss a few, not all, make you see how these errors work. Okay, you can read some of the rest on your own. They are quite easy to understand. Okay, so let me start. I want to measure the length of a pencil. So this is a pencil, okay? And I want to know the length of this pencil. So I place it on the meter rule, and it tells me I have 1, 2, 3, 4, 5. This 8, 6, 7, 8, 9, 10, 9. So on this meter rule, it tells me that I have this pencil 8.12, between 8.2 and 8.3, but where exactly I don't know. So I'll estimate, say between 8.22 and 8.26. Okay? Somewhere between there, between 8.22 and 8.26. Okay, not more than 8.26, okay, and not less than 8.22, okay. Then now take a difference. 8.22 minus 8.26 gives me 0.04, okay. Then I divide that by 2, 0.02, okay. So this becomes the error I'm going to use for this. So I'm going to take that 8.26 plus 8.24 divided by 2 also to give me an average. That gives me 8.25 centimeters. So the reading I get from there is 8.25 plus minus 0.02 centimeters. This is what we call reading error. So it's an error you get from reading a value with your eyes and estimating just from what you think it is. Just an estimate. So this is what we call reading error. This is how you get a reading error. So that's number one. We've done reading error. Okay. Now let's look at something else. I want to get the reading from a digital device. For example, I have a digital thermometer that gives me temperature. Okay. A digital thermometer like this. It has a scale I can see. It has 10.1, 10.2, 10.3 like that. It tells me the temperature at that point was like this. So this is the thermometer. Okay. It tells me the temperature was 10.2. Okay. Now it doesn't give me any error. But I say we always have errors. Now I have to find an error for this thermometer. How do I get an error for this thermometer? I first of all find the reading accuracy of this thermometer. It measures 0.1, 0.1, 0.1. So it's 0.1 degrees Celsius or degree Fahrenheit or Kelvin, whatever the scale is. So 0.1 degrees Celsius is the reading accuracy. Then I divide that reading accuracy by 2. Half of the reading accuracy is what we call the estimated uncertainty. Estimated uncertainty or estimated error. Okay? So half of 0.1, which is 0.05, that becomes my error. So it becomes 10.20 plus minus 0.05 degrees Celsius. This is what we call estimated error. You just estimate an error from the reading accuracy of the device. Mostly like a digital device that you cannot easily tell like from the reading error to get an estimate from, like that. Okay? So we've done number 2, estimated error. Now, let's say I measured the length of this table 3 times and I got 3 different readings, okay, for the length of that table. 3 different readings for the length of that table. I'm going to write the readings here on this table. I call them XI, 75.2, 76.6, 77.4 centimeters, okay? I want to get an error from these 3 readings. They are the same reading of the same thing. I mean, we are measuring the same thing but different values for the same thing. So how do I get an error from this? So the first step is to compute what we call the mean or average. It has a symbol X bar. It is given a summation of Xi when I goes from 1 to n divided by n, where n is the total number. N here is 3, okay? So this is the first reading, the second reading, and the third reading. So n equals 3, okay? So this is x1 plus x2 plus x3, like that, divided by n. So my x1 in this case is 75.2 plus 76.6 plus 77.4 divided by 3. This gives me 76.4 centimeters. So this is my x bar, my mean. After getting my mean, step 2 is to calculate what we call the deviation d, which is x minus xi minus x bar. I subtract the mean from each of this. 75.2 minus 76.4. That will give me negative 1.2. Okay? Okay? And then 76.6 minus 76.4 will give me 0.2. 77.4 minus 76.4 will give me 1. Then I do d squared, which is xi minus x bar all squared. Okay? That gives me 1.44. Okay? This will give me 0.04, and this will give me 1. Good. So the next step now is to compute what we call the I'm going to come here. I'm going to use this side. Sorry, I want to keep some of these errors that we're going to discuss. The root mean square deviation. The root mean square deviation, also called the biased standard deviation. The biased standard deviation. I'll tell you why it's biased. We'll talk of the real standard deviation. So this one is defined as I'll call it sigma b. Okay, sigma bias. It's actually the square root of sigma x minus x bar, okay, squared divided by n. Okay, so I sum the x minus x bar 1.44 0.041 square root of 1.44 plus 0.04 plus 1 divided by 3. So this will give us the square root of 1.48, so it is 2.48 divided by 3. Okay, that will give us 0.83 square root, something like that. Okay, 3 into 24 is 8. Yeah, about that. Yeah. So if we take the square root of that, it gives us 0.91 centimeters. Okay. So this is the root mean square deviation or the biased standard deviation. I'm coming to that. Let's look at step 3. Step 3 is the real standard deviation. The one that is unbiased, okay? The real standard deviation, okay? That one is the same, sigma, I'll call it sigma r, sigma real, or just sigma, okay? Is the square root of summation of xi minus x bar square divided by n minus 1. The difference is just n minus 1. So it becomes 1.44 plus 0.04 plus 1 divided by 3 minus 1 square root. That gives us 2.48 divided by 2 square root. Give us square root of 1.24. Give us 1.11 centimeters. Okay? 1.1 centimeters. So this is the real standard deviation. The standard deviation, the real standard deviation, is what we call the statistical error. So you see why I went through all of this, to explain to you what the statistical error here, number 3, here is. Statistical error. So we've discussed statistical error. So statistical error is the error you can attribute to each of the readings. So this is plus minus 1.11, plus minus 1.11, plus minus 1.11. Okay? I'll put a 0 here. So you can attribute to each of the readings statistical error. Okay? So this is the real standard deviation and the biased standard deviation. This is called real standard deviation because we'll explain that here. Because, for example, I told you, say we measure the length of a table 100 times. Say it goes from 95.5. You get different values between 95.5 and 99.5. Okay? You get different values from here to there. And let's say you get 100 different values. Every time you measure this table, you get 195.5, 95.6, 95.7, 95.8, 95.9, 95, 96, 96.1, like that. You keep getting different values. Let's say there are lots of them, up to 100. Now, what is the average of this? The average of all these values is this plus that divided by 2. So it's going to be somewhere here in the middle. Okay? That's the average you expect. Okay? 99.5 plus 95.5 divided by 2. Okay? That gives us 100.5 plus 94.5. Okay? 195. Okay? 195 divided by 2. Okay? So we'll do 195 divided by 2. So So this will give us 9, remainder 1, 7, okay, remainder 1.5, okay? Okay, is that okay? 97.5. Now, 97.5 centimeters is our average. So let's say if you measure this table more than 100 times, 200 times, you will still get values that are within this 100, between 99.5 and 95.5. So these are all the possible, what we call eigenvalues of the table, the length of the table. So even if you measure it 1,000 times, the value you get must fall between 95.5 and 99.5. And then we've gotten all the data that are necessary to measure the length of this table. But now I did only 3 times. I measured this table only 3 times. Only 3 times. How sure am I that those 3 times are not the first 3 in this direction? How sure am I they are not the last 3 in this direction? Or maybe I'm lucky they are the 3 in the middle. So I don't know which among the 100 possible measurements, if I measure only a part of what is supposed to be the total data taken, I measure just a few, how sure am I those eigenvalues do not fall to one side alone? So let's say I measure 3 times, I get 95.5, 95.6, 95.7. Then I take an average. That average will be a wrong average because it won't be the real average of the table because I've not measured the number of times I'm supposed to measure. So because of this kind of error, okay, we make the error more. We increase the error margin. That is why this is called bias. If you come here, the statistical error is the real one. When you divide something by n, or you divide something by n minus 1, which is greater, the one you divide by n minus 1 is greater because the denominator is smaller. So that is why we use the n minus 1 as our standard error, our statistical error, because it has a wider margin for our errors. In case of that kind of error, maybe your values were not enough, add some error, maybe it will get to the real average that is supposed to, when you put your plus or minus. Is that okay? So this one is divided by n, the biased one, and this one is divided by n minus 1 to just help us take care of possible errors that do not match with the number of eigenvalues or the number of values we're supposed to take for the complete data of this data set for the length of that table. Okay. Now, step 4. There's something we call the variance. Yes, it's not very useful here, but I'm going to mention it. The variance is just the square of the standard deviation. The variance is sigma squared. It's called the variance. So it is the square of the square root of sigma xi minus x bar squared divided by n minus 1. So you take the square of that, okay? So it's just the square of 1.11 squared, okay? So which is just what we had in the bracket, 1.24 centimeters squared, okay? So it's measured in centimeters squared. The standard deviation is measured in centimeters because it has a square root. The variance is the square of the standard deviation. It has centimeters squared, or the square of the unit you are using to measure. So that is step 4, the variance. Step 5 is something we call standard deviation of the mean. Standard deviation of the mean. So this simply means that I take the original standard deviation divided by square root of n again. This gives us standard deviation of the mean. I call sigma bar. 1.11 divided by square root of 3. Okay, this will give us 0.64 centimeters. Now, 0.64 centimeters is the standard deviation of the mean. It's different from the standard deviation. It's the standard deviation we got before divided by the square root of n, 3. This standard deviation of the mean is what we call standard error. Standard error. So we've known what standard error is. The standard error is the error we attribute to the mean alone. Remember the statistical error we attributed to each of the values we measured before. The standard error goes with the mean. The mean was 76.4. Now it's plus minus 0.64. So I put the 0 here to complete the significant figures. So this becomes the mean and standard deviation of the mean. Some people take the error to be the standard deviation of the mean. Some just take the standard deviation and they work like that. Okay? Depending on the choice of the instructor or the choice of the experimentalist that's doing the experiment. Okay. Now we've seen 4 different errors. Let's look at what we call the fractional error. To understand the fractional error, I'm going to show you something. Okay, I can wipe here. I can show you something. I want you to take a look at these two values with the errors. Take a look at these two values with their errors and tell me the one you think has a higher error, okay? I have 2.1 meters, okay, 2.1 plus minus, okay, 2.1, no, let me do this, say, 22 plus minus 22 plus minus 7 meters, okay? Okay? And then 3 plus minus, let me say 4, 3 plus minus 1 meters, okay? Okay, 22 plus minus 4 and 3 plus minus 1, okay? Let's analyze this, meters. Now, which of these readings has the highest error? What do you think? Tell me what you think. Which of them has the highest error? The first or the second?
The second one.
The second. You think this one has the highest error?
Oh, no, the first one.
Oh, the first one. Okay. So you think the first one has the highest error because it's 4, right? The error part is 4, bigger than 1. Okay. But now let's look at this. Let's think, that's what fractional error tells you. That's what we're discussing now. Fractional errors, okay? Take a look. I measure only 3 meters. I have an error of 1. I measure 22 meters. And I have an error of 4. Now think about it again. Which one has the bigger error? You measure 3 meters, 1, 2, 3, and your error is 1. 1/3 of your measurement. Then you measure 22.
Oh, the second one.
Okay, okay, you get it now? So sometimes we can be deceived by the error values, but we'll take the fraction, the error divided by the measurement, the measured value, it gives us a good, so 4/22 and 1/3, okay? This will give you 2/11, this will give you 1/3. So you see that this one is what? Bigger than this. So it tells you this one has. So from the fractional error, you can tell which error is more. So this is the use of fractional error. So it is the error divided by the value measured. The error divided by the value measured. Is that okay? The error divided by the value measured. Okay. So it's very important. Okay. And then now we've known what fractional error is. Okay. We're going to see the importance of this in propagation of errors. So we have relative error. Relative error is just true value minus the true value, okay, minus measured value. This is the relative error, okay? The true value minus the measured value, okay, is the relative error. And then we divide that by the true value. True value minus measured value divided by true value gives you what we call this definition of relative error. Okay, I'm supposed to give examples. It's a lot of information. Let's see how we go about that. Then percentage error is just to multiply. If you multiply this by 100, it's a percentage error. You can also multiply the fractional error by 100 to get a percentage error. Okay? So, relative error, percentage error. Absolute error is just telling you that take the absolute value of the relative error. So if I have true value minus measured value, sometimes the true value might be smaller than the measured value. It will give me a minus answer. So I take the absolute value. I just want it to be positive. So I'll ignore the minus. Okay? That's what absolute error tells you. Okay? They're just kind of connected, but just different perspectives of that. Okay? I don't want to keep going. You can read about the systematic errors and the erratic errors. Okay? Now I want to talk about propagation of errors. Okay? I'm going to clean the whole board. I want to talk about propagation of errors. Propagation I'm supposed to do some derivation here. I don't know if I might have the time for those derivation, but I'm going to explain. How do we add or subtract errors? So that's the first one. Addition and subtraction of errors. That's the first one. Then we'll go to multiplication and division, okay? I'm just going to be straightforward on this, okay? They have some derivation, okay? Maybe I might do them in a different lecture or send you a link to get the derivation, okay? But I don't think we'll have enough time today. Some of you are already sleeping, okay? We are tired. I'm getting tired too, but we can finish this quickly, okay? Now, say I have the length of an object, okay? I call it the length L, okay? Let me say L plus sigma L. So it has L plus minus sigma L. So it's the length and the error in the length. So it's 2 plus minus, say 2.0 plus minus 0.1. And the other one, the width, W plus minus sigma width, is 1 plus minus 0.2. 1.0 plus minus 0.2. So let's say these are all centimeters. Now I want to say, what is length plus width? Length plus width, let me call it Q. So it's going to give me Q plus minus some error in Q. The length plus width is Q. I can easily add 2 and 1. Length plus width. So Q is just 2 plus 1, which is 3. But how do I get the error in this addition? The error in Q. Do I add this plus this? Or subtract this from this? The error? No. So the error in Q is gotten from the sum of the square. So it's 0.1 square plus 0.2 square root. This is how we find error for addition. So even if I added something later, say L plus W plus another thing, I just square the error part and sum them up together. It gives me the error I need to add to the sum. So if it was L minus W, say this is S, it will give me S plus minus delta S. So S is just 2 minus 1, which is 1. So what is delta S? Delta S is the same. It's square root of 0.1 square plus 0.2 square. So whether you are subtracting or adding, the error part is calculated the same way. You don't put a minus here for subtraction. Okay, it's the same plus, whether you are subtracting or adding. Okay? And then the same when we go to multiplication and division of errors. So let's say I want to do L divided by W now. Let me call this P. So how do I calculate P? So it is just 2 divided by 1. This is P. But how do I get the error in P? Plus or minus delta P. So the error in P, okay, is calculated from fractional errors. So it is the error in L over L squared plus the error in W over W squared. It will give me the error in P over P. So error in P over P, P is 2 minus 1. I mean 2 divided by 1 because it's a division, okay? So which is just 2 equals square root of error in L over L, 1 over 2 squared plus error in W over W, 2 over, 0.1 over 2 and 0.2 over 1 squared. So I add those up, okay? This is 0.2 squared. This 0.1, so it's 1 divided by 20. So that's 0.05. So 0.0025 plus 0.04. Okay? So this is square root of 0.0425. Okay? That number will multiply 2. Because there's a 2 here. That number will multiply 2. Don't forget, so my error in P will be 2 times square root of 0.0425. That is what I will put as a plus or minus to the division. The same as multiplication. If it was L times W, it will be 2 times 1, and the error part will be calculated the same way as I calculated that of this. Okay? Error in the product over the product, the same way I did error in the division over the division equals that is the same way. Whether you're dividing or you're multiplying, you calculate the error the same way. Okay? And then the last but not the least is that of the powers. but we'll have a power for the error. For example, I say we have calculate the volume of a cube, okay, of sides 0.2, or let's say of sides 2 meters. So we'll have a cube like this, okay. So this is a cube, say, of side 2 meters. So what is the volume? So volume is just L cube. So this is 2, I said plus minus 0.1 meters. So I have the length and error in length, okay? So how do I get the error in the volume? So I want V plus minus sigma V. As I have L plus minus sigma L. How do I get V plus minus sigma V? Now it's a power, L cube. So you don't say L times L times L and compute this separately. You get an answer that's slightly different. So for powers, we differentiate. So we say dV, okay? We say dV dL equals, we differentiate this 3L raised to power 3 minus 1, okay, which is 3L second. So dV is my error in V, dL is my error in L, equals 3L second. So my dV, my error in V, equals error in L times 3L second. I know my error in L, 0.1, times 3L second, 3 times 2 second. So that's 0.1 times 4 times 3, 12, 1.2. So my error in V is 1.2 meters cubed. Now, what is the volume? The volume itself is L cubed, which is 2 cubed, which is 2 times 2 times 2, which is 8. And my error in volume is that. So V plus minus error in V is 8 plus minus 1.2 meters cubed. So to 8.0. So you differentiate. After differentiating, you call your differentials the errors. And then fix the length. This is the error in length, which you already have. You have the length. From there, you get the error in volume. Then you calculate your volume itself from the L cube. And then you attach this error from the volume to that to get the volume plus error in volume. If it has a power. This is if it has a power. Okay. Yeah, I was supposed to prove all this to you, how these formulas were gotten, and how sometimes the powers change if it's independent. If they are independent of each other, they are dependent of each other. But right now, I don't want us to go into that right now. I think we should just be fine for now. Okay. Just before we leave, I just want to make a few comments about normal distribution, which is also known as a Gaussian distribution. I might not be able to take examples here because we're already exhausted for the day. So a normal distribution is a distribution that when you plot it, it looks like a dumbbell like that, okay? It's symmetric about the axis, the origin like that. So here we can have a distribution, say the test scores in math. So say in math out of 100, 85, 86, 81, 70, 68, 91, 92, 90, like that, say of 30 students. So you write all their scores, okay? Then you want to check if those data behave normally, if they behave normally. So what you do is, there are two ways to check for a normal distribution. You plot like what we call the histogram for this distribution, one for each student. So you have like 30 of them, like that, okay? So you're going to have something that looks like this. So if it's a normal distribution, it's going to look like that dumbbell shape, symmetric about the origin or about that. Sometimes it is skewed to the left or skewed to the right. That is not very normal. Okay? Okay? So what do we mean by a distribution being normal? Okay? Diagrammatically, we see what it means, that these histograms, okay, or bar charts, depending on what you plot. Okay, so you should learn how to plot a bar chart or histogram from a data like this. Okay, you're gonna get the class mark and things like that. You plot a table, and then you get the points, the class points, and then you take the frequency. How many people had 86? How many people had 85? Like that. Okay. Now, when you plot that, then you check if it looks like a normal distribution dumbbell curve. That is one way to check for a normal distribution. Another way to check for a normal distribution is that you check all your data, you compute your standard deviation, which is normally calculated from the origin sigma, standard deviation sigma, like that. Then you're going to have 2 standard deviation, 2 sigma. And you can have 3 standard deviation, 3 sigma. So this is 2 sigma, and you can have 3 sigma, okay? So check if 68% of all your data fall within when you add sigma to your mean, x bar. So your x bar plus minus sigma, check if the mean plus, say your mean was 70, your standard deviation was say 10. So check if 70 plus 10, 80, 70 minus 10, 60. Check if 68% fall within 60 to 80 range. 68% of all the data you measure. So if you do that, you see that all the data you measured, calculate them, maybe out of the 30, you see that 25 out of the 30 fall within that range. So 25 over 30 times 100 will give you that percentage. So you see it's already more than 68%. So it means it's going to be a normal distribution. Then also check if 95% fall within 2 standard deviations. 2 standard deviations. So x bar plus minus 2 sigma. So that's going to be 70 plus minus 20. So it's going to be 70 plus 20, 90, and 70 minus 20, that's going to be 70 minus 20, 50. So check if 95%, which is almost all, okay, fall between those scores, 50 to 90. That's another way to check for normal distribution. Okay, then 99.7% should fall between 3 standard deviations. So x bar plus minus 3 standard deviation. Check if almost everything falls there. So once you see that everything falls there, there is no need for you to sketch the normal curve or the histogram. So you can use the histogram to verify if a distribution is normal, or you can use this percentage method to see from calculating the standard deviation. Okay? And what do you mean normal distribution? I'll explain easily. For example, if I give you a coin, I say flip a coin, you cannot tell me, okay, a priori to flipping the coin if it's going to be heads or tail. So flip once, you get head. Flip second time, you might get head or tail. But when you keep flipping a lot of times, flip, 100 times, you cannot tell me all the 100 will be heads or all the 100 will be tails. That's very rare. That is not a normal distribution. It's a very abnormal. So for a normal distribution, when you flip that coin up to 100, 200 times, around 50 will be heads, around 50 will be tails. Maybe 49 or 48 heads, 52, 51 tails. Is that okay? That is a normal distribution. So a normal distribution is a distribution that we expect that it's going to behave like at the center. You're going to see it's equally distributed. Okay? Some here, some there, equally distributed. Okay? So that's what I mean by normal distribution. It's what we expect when we take a lot of data. So when you do some analysis, you expect a normal distribution, you don't get it. So it's maybe you didn't use enough data set to do it. Or maybe there was some error there. Somebody gave a wrong value, which skewed the distribution a little bit. So I'm just going to end with this, and then we'll call it a day for the introduction class. Thank you for your patience, and see you next class. Yes.